Okay, number 3, we're given z equals x squared plus y squared, x squared plus y squared is 1, and z equals 0. Let's try to visualize what's happening here. Z equals 0 is the xy plane, so that's where we're starting. X squared plus y squared equals 1. Well, in the xy plane, that's a circle of radius 1 centered at the origin. Try to draw that in there. But since there's no z variable, we're free to wish this up and down. So this is going to be a cylinder of radius 1 centered at the origin. That's what that's going to be. Z equals x squared plus y squared. Well, that's our friendly paraboloid. So we imagine we've got the base of this thing is z equals 0. That's the xy plane. And I've got this paraboloid, and I've got this cylinder that's going to come up and sort of engulf part of the paraboloid. So the volume we're looking at is the solid that's outside the paraboloid but inside the cylinder that's above x squared plus y squared is equal to 1. So a good base then is going to be in the xy plane, and that's going to be over the unit disk. That's our region R. X squared plus y squared is less than or equal to 1, which means that our height then, well, that's going to be z. The coordinate system of choice, well, for this, it's going to be polar. So polar plus z is going to be cylindrical. So we need to convert this. Our volume is going to be a double integral over the base times an integral over the height, 1, the height's dz, and we'll set up the base here in a minute. Okay, so r in polar coordinates, we've seen this several times, 0 to 2 pi, 0 to 1. That's a disk of radius 1. What's the height going to be? Well, for a fixed r and theta down here in the plane, what does the height run between? Well, it runs between here, z equals 0, up to the paraboloid, z equals x squared plus y squared. So z equals 0, that's the same in both cylindrical and rectangular coordinates. But z equals x squared plus y squared, well, that's z equals r squared in cylindrical coordinates. Then we have dz, and then for the area differential in polar coordinates, we have r dr d theta. So that'll do it then for number 3. All right, number 4. We're given x equals 1 minus z squared, x equals z squared minus 1, y equals 0, and y equals 4. So let's see what this looks like. Well, y equals 0 is going to be the xz plane, and y equals 4 is going to be 4 units out. So these are constant. We're just y is going to be running between these two values. And if you look, once again, as we've seen before, we've got a free variable here. The y is free in both of these cases, so whatever curves these are, they're just going to be copied from y equals 0 to y equals 4. So that tells me that this is probably going to be the height variable. And it's very hard to draw in the xz plane, and so I'm just going to take a snapshot of what's going on here in the xz plane, because this is where the base then is going to be. X equals 1 minus z squared and x equals z squared minus 1 are both parabolas. One of them opens to the right and one of them opens to the left. So this is x equals z squared minus 1. This is x equals 1 minus z squared. So this area in between is going to be our base. So I need to find where these things intersect. Shouldn't come as too much of a shock. They intersect when z equals plus or minus 1. So as always, the volume equals the integral over the base times the integral of the height. The height in this case is the y. Oops. And the base is going to be something in the xz plane. So the order of integration that probably makes the most sense is chopping up the z-axis and then going from this x to that x. So we're going to chop the z up from -1 to 1. For a fixed z, the x runs between z squared minus 1 and 1 minus z squared. And now the height in y goes from a constant 0 to a constant 4, dy, dx, dz. So that'll do it then for number 4. Finally, number 5, we're looking at the solid which is below z equals 4 minus y squared, above z equals 3y, and between the planes x equals 0 and x equals 2. Well, this is the second or third time we've seen this. The constant bounds on the x and the fact that x is free in these two equations means we're going to have the base in the yz plane. And then the x is just going to serve as the height. So let's just graph what's going on in the yz plane. Z equals 4 minus y squared. That's a downward parabola. Z equals 3y is an increasing line. So as always, we have to find out where these things intersect. So z equals 3y equals 4 minus y squared. In other words, y squared plus 3y minus 4 is equal to 0. So you get y equals -4 and y equals 1. And so we're going to volume V, double integral over the base, integrate the height variable. The height in this case is dx. The base is going to be either dy dz or dz dy. We'll make that determination now. Since z is given as a function of x and y, or excuse me, a function of y, it makes sense to chop up the y's from a constant -4 to a constant 1. And then we'll, for fixed y, what's the z run between? It runs between this line and that parabola. So that line is z equals 3y to z equals 4 minus y squared. And the x here is constant from 0 to 2. dx, dz, dy. And so hopefully one of the things you got out of this checkpoint quiz is that if you have a variable that's free, you get those cylinder shapes like we talked about in Calc 2. And if the variable's free is the same variable that's giving you constant bounds, then that tells you that that's going to be the height variable, and then the base is going to be happening in the other two planes. So that'll do it for quiz 16.